one of the consequences of the pressure being greater at depth is what we call the buoyant force. It's the force that helps support us whenever we're in liquids. And it can be in water, but it's also in air, right? When you have hot air balloons that rise. And the basic idea is this. If we look at the pressure points from all sides, like pushes like this. Liquid wants to fill the space. If this is a box, right, like that, then the pressure pushes from all sides, and on the top it pushes like this, but on the bottom there's a bigger force because we're deeper, right? The pressure is deeper, so actually on the sides the pressure gets bigger on the sides further down. And so we have this pressure at the bottom compared to the pressure at the top. And it's this differential in pressure, that's one way to think about sort of what causes the buoyant force, the lifting force. So what we want to do, if we know this is the area, right, of the top and bottom, we'll go ahead and just make this an even box, then we would say this net force up is going to be the pressure at the bottom times the bottom's area minus the pressure at the top minus the area there. And so if we go ahead and plug in this equation, and this would be pressure at the bottom, whoops, I'm going to set up an equation for the pressure at the bottom. Okay, so plugging this in, I have P0 plus rho g, now I need an h, so I'm going to have an h to the bottom, h bottom times A minus pressure 0 plus rho g h to the top times A. So this is going to be the height, the depth below the water to the top. And so I've got some A's. Notice that this P, the pressure at the top of the water, that's this P0, times A shows up positive and then a negative, so those cancel out. So this force up is going to be just rho G HB times A minus rho GHT times A. And so both of these have rho and G, so I'm going to factor that out. And I'm going to have, oh, and A as well. And I have HB minus HT. And that's the force up. And this HB minus HT is really just the height of this box, right, is our height overall. So we can just call that our height. And so this becomes rho G A times H, but that's the volume of the box, right? So the force up, which is what we call our buoyant force, is our force up, our force buoyant, is equal to rho of the liquid that you're in, water, air, whatever it is, times G times the volume of the liquid displaced by your object. Or if you prefer, the amount of the volume in the liquid. Okay, and the reason that matters is, of course, some things float. So something that's floating, right, here's our water, here's our object that's floating, right, then this volume is what we put into this liquid. So we would say that if it's floating, then we have that mg is balanced by this FB. And so we have, here's our force diagram redrawn again, mg. So that's the weight of the object. The FB that's up is rho of the liquid times G times the amount of volume in the liquid. So the part that's submerged, the fraction that's submerged, if you like. And that would be equal to your mg when you have something floating, because it's in static equilibrium, so the forces do balance. And so this buoyant force depends on the volume of the object and the density of the liquid. Another way to look at this, though, is to say the density of the liquid times the volume of the liquid is mass. So some people write it as mass time of the liquid displaced times g, or they say it as the weight of liquid that the object displaces. That feels a little odd that your force is equal to a missing amount of water, but it probably makes some sense, because if water were in this space, then this pressure underneath would be supporting that water. So if the water's suddenly removed, well, then you've got some capacity to lift things up. So if you prefer to write it as weight of the liquid displaced, then that's fine. But I think to calculate it, it's usually easier to find this. And so this is how we figure out whether things are going to float or not.